Okay, good afternoon, everyone. Today we look at diode circuits. The first and one of the most important applications of a diode is as a rectifier. Okay, rectifier circuit. Now, the word rectifier in the English language means that there is a problem and we are rectifying it with a solution. But in this case, it is nothing like that. Rectification simply means we are converting AC to DC. Okay, that's all it means. And a diode is one of the most important applications because all of power transmission, generation and power transmission is all in AC all across the world. There's a generator, it's a rotating, so it's a rotating stator with winding that is rotating inside a magnetic field, and it generates a sinusoidal waveform, right? So that's AC, alternating. And all of the appliances, electronics, devices that we use in everyday life, they all run on DC. Okay, every single thing runs on DC. Whether it's your mobile devices, whether it's the projector, monitors, computers, everything runs on DC. So AC power generation and distribution is far simpler and more cost efficient than doing it over DC. So rectification, again, is an application of the diode to convert AC to DC. The opposite, converting DC to AC, is inversion. That device or that circuit is known as an inverter. There are inverters that have become very popular. Many of the modern cars nowadays come with a 120 volt power outlet. So there's an inverter that does that. In our lab room 112, there is an inverter, vehicle inverter that's lying on one of the shelves. So next time you come to lab, if I don't remember to do so, someone please remind me and I'll bring it out and just, put it on the center table for students to view. All right, diode half wave rectifier. So half wave, as the name suggests, is only going to rectify half of the AC waveform. When we say half, we are referring to one full cycle of the waveform. So one full cycle of the waveform is one time period as a positive half and a negative half. Okay, so a half wave rectifier will either rectify the positive half or the negative half, depending on our requirements. So what we are going to do is we are going to use ideal diode analysis or ideal diode model to make a quick analysis, right? So ideal diode model to perform a quick analysis. So let's draw the circuit for the positive half cycle. The positive half cycle, the top terminal is plus, bottom terminal is minus. Diode anode is connected to the positive terminal, hence the diode is forward bias. We replace it with a short circuit. So diode D1 is on. This is simply the load resistor RL. Okay, simply a generic representation of the load. Load could be anything. And diode D is on. And current flows in this direction. Point of entry is from the top. This causes a voltage drop plus minus VRL. Make sense? Negative half, the exact opposite happens. We can represent the negative half with a plus and a minus this way. Bottom terminal is plus, top terminal is minus, which renders the diode open. Reverse bias, hence open circuit. And we can say diode D1 is off. Okay, D1 is off. So in the positive half cycle, the output voltage VRL, V out, so VRL, let me just write down VO, output voltage, is equal to the input voltage V in. Whatever you apply at the input is obtained at the output. If you apply a sine wave, you get a sine wave at the output. Apply a square wave, you obtain a square wave at the output. If you apply a DC, flat DC voltage, you'd get a flat DC voltage at the output. Okay, whatever you apply, you receive at the end. The negative half cycle, obviously, V out is equal to 0 because it's cut off from everything. So if we plot the waveform, this is the input waveform, this is the output waveform, and let me do this time period is for 60 hertz sine wave, which is our power outlet. Okay, power outlet. So positive half cycle, diode is on, and so that is represented here. Input is equal to output. I'm sorry, output is equal to input. And negative half cycle, diode is off. Right, let's take a pause. Let me know if you have any questions. Any questions? Did it all make sense? Okay. So if you look at the output waveform, what questions come to mind? We say that this is AC, and we say that this is DC. I don't have a gun. Sure. Slightly higher level question, though. That's a very valid question. Slightly higher level, though. The first question that would come to my mind is, how can we consider this as DC? That's not DC. It's still it's still varying its value. How is that DC? And you're absolutely right. It's not quite DC. Most authors, most books will refer to it as pulsating DC. Okay, pulsating DC. I simply like to call it as pseudo DC, but I'm not a famous author, so can't call it after myself. But it's my classroom, so I can use pseudo DC. Anyway, so as your question asked, like there should be a DC value for this, and there is absolutely. We can find a average value for this that would count as the equivalent DC value of this pulsating DC waveform, right? But it's not quite DC. So this is the first step in a number of steps that is used to create a power supply. Okay, so even the simplest of power supplies at least have 4 different steps. Okay, 4 separate steps. Modern power supplies actually have more than 4. But the obvious downside is half the time it's off, And so we are losing all of that energy that is coming from the input. So we go to the next circuit, which is the full wave rectifier. As the name suggests, it's going to rectify the full cycle, hence a full wave rectifier. I don't particularly like this diagram. This is from the textbook, so I have it here. I like this. This is what I learned with, and this is what I teach. Far simpler schematic. Essentially the same. Okay. You have diode D1 on top, diode D2 on top. And now, as the name suggests, one diode each will be on for each positive and negative half cycle. Oh, one more thing. Sorry, about the half wave. Diode is pointing towards the right. Circuit schematic, right? Anode is pointing towards the input supply. What happens if you flip it? You get a negative output. Okay? If you flip the diode in a half wave rectifier, you obtain a negative output because now the diode is on in the negative half cycle and it's off in the positive half cycle. So because of our reference, it'll turn out to be negative, which you will see in a few slides, the application to generate a dual power supply. All right, full wave rectifier. The previous section, I asked if everyone was familiar with this symbol. Y'all didn't study this in 115, right? So let's go to a sidebar. What does this symbol remind you of? Surely you studied this. Inductor, right? It's an inductor. Now, an inductor can be an empty air core because it's a coil, it's a winding, right? It sets up a magnetic field. If there is only air, if there is no core inside the winding, we say it's an air core winding. The magnetic field is weaker. And if you stick a ferromagnetic material inside the winding, now the core is some sort of ferromagnetic material that permits the creation of flux lines. And so the magnetic field is a little bit stronger. Operating principle of an electromagnet. Now, what is this? This indicates there is, okay, so inductor on the left, inductor on the right, two parallel lines in the middle indicate it's a core, C-O-R-E. Okay, iron core, most laminated iron core for the most part. In this device, it's a very important device, which is known as a transformer. These are not from Cybertron. But they play a very important role in power generation and transmission. Okay. So as I said, sidebar, this is a big topic by itself, so I'm going to try to condense it in a few minutes. When you have an inductor and it's wound around a core, you have an electromagnetic field. If you supply energy at the input of that inductor, it's going to absorb that energy and store it in that electromagnetic field. Right? It's an energy storage device. Now, if you take a second coil and wind it around the exact same core, now the magnetic fields of both inductors are linked. Okay. This is the input side is referred to as the primary winding. The output side is referred to as a secondary winding. Okay. The reason this is very important is because all power generation is AC. All power generation is AC. You have a rotating winding inside a magnetic field. Sinusoidal waves are generated. It's depending on the size and the design of the generator. certain voltage and certain current would come out. Okay. When you want to transmit this voltage or long distances, this voltage needs to be stepped up, increased in size. And the transformer is the device that allows us to do this with simple ease. Transformers have interlinked windings. These interlinked windings have a turns ratio. An inductor has a number of turns, N. I'm assuming at least you're familiar with that, perhaps. Okay, so inductor has a quantity known as N. The N is basically the number of turns that the coil has. Okay, so depending on our requirement, the transformer, which has two linked magnetic fields, can either step up the voltage or step down the voltage. So at the generation and transmission end, the voltage is increased, so it's stepped up. And at the receiving end, meaning when the lines arrive at the outside the city or in the consumer households, it's now stepped down. Okay, so the voltage is decreased. And I'll explain how and why. So the input is applied to the primary coil. Primary coil stores it in its magnetic field. It is now linked to the secondary magnetic field. Energy is transferred over to the secondary side. Secondary side is converted back into electrical energy, and then it's sent out. Okay, so you can have a step up or step down transformer. So long distance transmission lines, long distance power is always transmitted with AC. Okay, because AC power generation is very easy or easier than DC. And then here's one of the reasons why we need to increase the voltage when you transmit electrical power over long distances. Electrical power is the product of the voltage and the current. Standard equation, V times I. In terms of resistance, power is also V square over R and I square times R. Okay. R is the resistance. Equation for resistance is rho L over A. It's directly proportional to the length of the material or length of the conductor. When you have a 100-foot extension cable or 200-foot extension cable, 200 feet, the resistance is small. It's not going to drop the voltage a lot. Let's say if I plug in a 100-feet extension cable into the power outlet on the other side of the room, and I bring it over 100 feet away, voltage might drop maybe like half a volt, perhaps, if that. But when you're sending transmission, when you're sending power or electrical lines that are hundreds of miles long, that conductor will have some resistance. And that resistance will result in electrical power loss, which is lost as heat. That power loss is square of the current. So if you want to transmit electrical power over long distances, a lot of the power is lost during transmission. So you need to increase the power before you transmit it. To increase the power, you only have two choices. You either increase the voltage or you increase the current. If you increase the current, your power losses increase by a factor of I square. So better choice is to increase the power, increase the voltage rather than increasing the current. To increase the voltage, we use a transformer. We use a step-up transformer. So electrical voltage using transformers is stepped up to tens of thousands of volts. Okay, 22 kilovolts, 30 kilovolts, 40, 50 kilovolts, I believe. So that's like 20, 30,000 volts. That's what it's a high voltage AC lines, HVAC, not HVAC units. HVAC would be high voltage AC lines, AC power lines. And so you would have seen these big towers that are going across the mountains that are carrying these big transmission lines. Those are high voltage transmission lines. As they get closer to a city, that voltage is now stepped down to what is required. So that 30,000 volts is stepped down to perhaps 5,000 to like 1,000 volts. There's a substation. Even on campus, there is a distribution facility, and then power is stepped down to like hundreds of volts. If you go around campus, you'll see some wooden fences sometimes. It will not have a gate, or if there's a gate, it's like do not enter, do not do anything, do not slap anything, like any kind of notice on this wall. Those have transformers behind them. Those transformers are huge. Okay, they step down the voltages, they're sent to the buildings. If you go down any residential street, you might have sometimes seen a light pole, not light pole, like the electricity distribution pole that has a cylinder around it. Anyone ever noticed that? That cylinder is a transformer. And that transformer will have like 3 or 4 lines running into each individual home. So the transformer is taking hundreds of volts and stepping it down to like 110 volts and sending it into each residence. So that's a step down transformer. Okay. So very important device, without which none of nothing that we're using today would be possible. So lots of researchers over the years have done research on transformers. The first working prototype of a transformer that is credited it was credited to 3 Hungarian researchers back in the late 1800s. Obviously, there were a lot of people who came before them who were working on this. Tesla was one of them, and he was the one who came over from Europe. So he took the design of the Hungarian researchers and then, I guess, made some modifications to it. And then a lot of other researchers did the same. And, here we are today, over 100 years later, enjoying the benefits. So transformer is a very important device. That's also the front end of every single power supply that we use today. Yeah, the front end, there's always a step down transformer. We use mobile phone chargers and tablet chargers, which are 5 volts. Power outlet is 120 volts or 110 volts, right? So you can step it down from 100 volts all the way down to 5 volts. We need a transformer to do that. Okay, without which it would not be possible. One more application. How many of you have wireless charging devices? Cell phones, tablets, smartwatch. You may have at least seen a video or a picture, or even heard about it, even if you have. My phone doesn't have a wireless charger. But on the back side of your smartphone or your device is a coil. It's an inductive coil. That's on the back side. And the charging mat has a coil embedded inside it. When you plug the charging mat into your power outlet, that power outlet is converted into a step down, and it's converted into a certain voltage depending on the device, obviously. And that charging mat has a magnetic field. So the magnetic field is right above the surface of the mat. When you take your device and you plug it down on top of it, the coil on the back of your smartphone is now linked to the magnetic field of your charging mat. So the 2 magnetic fields link up. Energy is transferred from the power outlet to the charging mat inductive coil. From there, it goes to the magnetic field. Then it goes into your smartphone, and the coil inside your smartphone converts it into electrical energy. That charges the battery. And that's why if you have a thick case on it, it's not going to work, because the thickness or the distance between the magnetic fields will prevent the 2 magnetic fields from linking up. And so if it doesn't link up, energy is not going to be transferred. It needs to link up. Also, if you don't place it correctly right on top, it's again not going to link up. So it's 2 separate inductors. The magnetic fields need to link up for wireless charging to work. That was one of the ideas that Tesla had. So wireless charging can be attributed to some of his work. He actually had fantastic ideas. One of his ideas was true wireless power transmission, meaning you would not need power outlets. You would simply send electrical power through the air. But not feasible because you have I square R losses. All right, coming back here from our sidebar. So depending on the turns ratio meaning the turns of the inductor on the primary side and the turns on the secondary side, you can have step up or step down. On a power supply, in a rectifier power supply, this is step down. Yeah, it's step down. Now, the special thing about this transformer is that there is a tap in the secondary winding. It is approximately in the center. So it's known as center tapped transformer. That was a special thing about this transformer. So center tap transformer. And what the center tap does is it creates two separate power supplies, essentially speaking. So if you have something like this, it's going to create two separate power supplies. If your input in a regular transformer, if your input is 10 volts, your output will also be 10 volts. In a center tap transformer, if your input is 10 volts, you have two outputs of 5 volts. Okay. The center tap allows us to have two independent, not independent, but two separate power lines, one for each half cycle. Make sense? Operation is not difficult. So again, we'll use the ideal diode model. And then in the positive half cycle, the transformer can be represented. Oh, not that. You have plus at the top, minus at the bottom. Same thing for the secondary coil on the below the center tap. So diode D1 is forward bias, replaced with a short circuit. And diode D2 is reverse bias, so replaced with an open circuit. So D2 off and D1 on. Current will always, so for a supply, current is always going from minus to plus. So current goes in this direction, pathway goes here, goes down, and enters the resistor from the far left or far right. So it causes a voltage drop with a polarity plus minus VO. So in the positive half cycle, VO is equal to V in. And whatever you give to the input for the positive half cycle, you obtain in the output. Actually, the analysis is the same as the half-wave rectifier. Right? Yeah, all you have now is two separate lines, but they are interlinked. In the negative half cycle, the exact opposite happens. And now it's minus plus and minus plus. So diode D1 is off because it's reverse bias. And D2 is the one that's on because it's forward bias. If you follow the sign convention, we would see that the current is still flowing in the exact same direction. IL causes the voltage drop in the exact same polarity. And so again, V out is equal to V in. But in this case, we are plotting V out across the resistor. Right? It's not sharing the same current as the diode itself, not the two diodes. It's two different. So the voltage across the resistor is positive in both directions. I mean, sorry, for both half cycles. And hence, we obtain a waveform that looks like this. This is when D1 is on. This is when D2 is on. So both half cycles are rectified, and you get positive output for both. Let's take a pause. Think over it. Let me know if you have questions. Sure. Yes. Secondary coil. Yes. That's just the tapping. Yes. So the question being asked is on the secondary side, because of the tap, is it being split into two? Well, the answer is yes. Okay, let me understand. I think the question being asked is, can we have multiple taps on the output side? Or can we say it's like a 3-terminal component, the transformer? Yes and no, because the transformer as such does not. Actually, I have never thought of it, but yeah, you're right. I mean, we could call it a terminal. And the answer is yes. In this case, a center tap transformer can be said to have 3 terminals at the output. I had actually never thought of that. But my next point I wanted to say was there are transformers with multiple taps. I actually had a DC power supply. This is about 32, 33 years ago. And the power supply had a manual switch on the front. Click, 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 click. 1.5 volts, 3 volts, 4.5, 6, 9, 12, 15 volts. So multiple positions on that switch. One day I just opened it up. I just wanted to see what was inside. So I opened it up and I see that at the switch, you had these multiple positions and each one had a wire that went into the transformer. So the transformer had multiple taps, one for each of the settings on the outside. And so that was like a multi-terminal transformer, if you will. Yes. So let me see if I understand this correctly. Okay, repeat it one more time. Okay, so question being asked is if the output is equal to the input, then how is it stepping it down? Okay. So the step up or step down occurs right at the transformer itself. After that, the diode, in this case, it's the ideal diode model. This is like skipping over 2 slides. But real life, obviously, a diode will require 0.6 or 0.7 volts to turn on. So if you want a 5-volt output, then we have to add in every single diode voltage drop for every single half cycle. So in a half wave rectifier, it would be 5.6. In this full wave center tap will also be 5.6. So it would step down from 110 volts to 5.6 volts. If you are just talking about the diodes, then then there's another explanation of the other additional components, and then we'll talk a little bit more in depth. But the answer is, yeah, if you want to account for the diode drop, the transformer is going to step it down and then account for the diode drop. So circuit designers will actually do that. Yes. The polarity on the tap relies on the windings of the inductors. Yes, there is. So for further reading, I would suggest and recommend you have the entire textbook at your disposal. There are some excellent chapters in the textbook. There is a separate one devoted to, so the one in the inductor will have something about transformers, like linked windings and stuff, but there's a second chapter at the end, I believe, that talks a little bit more about magnetic circuits. And so it'll have some equations about turns ratio, and there'll be some derivations that will go through and explain how the transformer would work. Yes. So for our purposes, as in for this class, I would like to say I'm never wrong, but that would be wrong. You're talking about these polarities? That's always true. So the polarities that are being asked are about these. I'm assuming you're talking how it's coming out in a serial fashion, right? Plus, minus, plus, minus, plus, minus. That is very true. Yes. The windings, that's one of the phenomenon that occurs naturally, yes. So if you tap it in there, it splits it up into two independent coils, and the polarity is plus, minus, plus, minus, plus, minus. Obviously, when it goes to negative half cycle, it becomes minus, plus, minus, plus, minus, plus, minus, plus. So it always follows that sequence. Yes, and that is what allows us to do this. Yes. So the question being asked is if both the D1 and D2 or just D2. So if just D2 was flipped, then what would happen? And I believe you answered it yourself, is the negative half cycle, we would obtain a negative output. So we would obtain, that would be very interesting actually. The positive half cycle would have plus voltage, negative half cycle would have negative voltage. So if you had like an LED connected to it or something, two LEDs connected, in that, then it would be like alternating, flipping. But yes, that's the answer. On a breadboard, tapping an inductor, well, wouldn't be possible unless the inductor is open. Yeah, I would not be able to do so. But obviously, center tap transformers are more expensive than regular transformers just because of the extra work that's required. And so, to negate that point, we use something known as the bridge rectifier. The bridge rectifier is also a full wave rectifier. If you take a look at the circuit diagram, there's about 12 minutes left, so I'm going to do this in a little bit of a higher pace. If you look at these diodes, D1, D2, D3, D4, the resistor spans kind of like a bridge between the two outputs. So the four diodes, if you notice, two are pointing up and two are pointing down. The point where the two cathodes meet and the point where the two anodes meet is where the output is connected. Anode is the p-type material. It's the negative end of the output. And cathode, the n-type material, is the positive end of the output. And you will see why that is when we perform this analysis. Okay. So you have four diodes. Just by intuition and logic, it makes sense that two diodes will be on for positive half, two diodes will be off. I'm sorry, two diodes will be on for the negative half, right? So again, let's use ideal diode analysis. Or ideal diode model. And in the positive half cycle, I can say that if you look at the circuit, which diodes are on and which are off? So you have plus at the top, minus at the bottom. D1 and D3 are on. Yes, because the anodes of both ends are pointing towards the, anode of D1 is pointing towards the plus, cathode of D3 is pointing towards the negative. So here it's D1 on, here it's D3 on. If you look at the current, again, using the passive reference configuration, current's going to move in this direction. it's entering the resistor from the left, causing a voltage drop. The plus on the left, minus on the right. Current is entering through the left. Point of entry is always positive, causes a drop. Point of exit is negative. Negative half cycle. The opposite happens. D1 and D3 are now off, and D2 and D4 are now on. So to be minus plus this way. That's a good way to represent it. And then we have D2 that is on. So let's do it this way. It's D2 that's on. And here, this is D4 that's on. If you follow the current using passive reference configuration, current's actually flowing in this direction. It is again entering the load resistor from the left. So the voltage drop across the resistor is in the exact same direction. So V out is a rectification of the negative half cycle. We still obtain a positive voltage. So without using a center tap transformer or two independent supplies, we now created a full wave rectifier. So this is the input. This is the output. Okay. Yes. Yeah, we don't need to use that. Anybody hear of the term called wall wart? Wall wart? Wall as in walls, and wart as in W-A-R-T. Those were that was a nickname given to all of these chargers and adapters that will plug into the wall. So the mobile phone chargers and the tablet chargers that we use nowadays, they obviously have the cables. So it's a USB port, so you just plug in a cable separately. But previously, all of these had cables attached to it, internally connected, and you'd plug it into the wall outlet. And so, depending on your perspective, they look like ugly warts on a wall, and so they came to be known as wall warts. These are all power supplies. The transformers in those would be about the size, my palm, about cube this size. Okay, and they would be heavy because it's a transformer, heavy metal winding, right? Modern chargers are very lightweight because they use a different kind of design. Okay, so modern chargers, they first have a diode. They rectify the high voltage 110 volts AC into a pulsating DC, gives it to a capacitor, filters it out, high voltage capacitor, and then it's fed into a transistor oscillator. So it creates a high frequency AC signal. And the high frequency AC signal, again, there's just laws of physics. If the frequency is high, the transformer will be small. And so a really high frequency AC signal, which is about a few hundred hertz or a few kilohertz, the transformer is very, very small and very lightweight. And so now the output of the oscillator is fed into that transformer. The transformer output is now stepped down and fed into a rectifier diode and then rectified again. And that's why we have these lightweight chargers. Okay. I'll try and get some images for next time. If you ever take a look at your chargers, it will always say input 100 volts to 240 volts and 50, 60 hertz, 50 to 60 hertz, meaning you can use it anywhere in the world. And that is one of the advantages of this modern design. Previously, we had these chargers in my day, and that wasn't too far off, just like 10, 15 years ago. We had these chargers, and those charges were only meant, if it's 110 volts, you could only use in North America. If it was 200 volts, you could only use it outside of North America. You could not use in other, in either place. Do not bring something from outside and use it here because the transformer input is fixed. Now it's not so. Yes. So that's the next point. The question being asked is, what if you weren't using ideal diodes? That's a very good point. So if you use the offset diode model requires 0.6 volts to turn on, 0.6 to 0.7 volts. Book uses 0.6, so I'm going to stick with 0.6. So it uses 0.6 volts for diode to turn on. So your input must account for this voltage requirement. If you require 5 volts at the output, your input must be 5.6. Bridge rectifier, it must be 6.2. So 1.2 volts. It needs to account for all the diodes in that circuit line. Yes. So if the voltage at the input decreases, is that the question? That would have to be like, we only require 0.6 volts to turn on the diode. So there would not be a possibility where the voltage would go down below 0.6 volts. But it's a fair question. What if the input voltage is not enough to turn on the diode? So it's not that we would not feed it just 5.6. I'm saying it has to be greater or at least 5.6 to account for the diode. And there are many other factors. So let me hold that question because I'm going to skip over this for now. We saw that we have the output is pulsating DC. That's not what's quite required. We want a flat line, right? So we attach a capacitor at the output. The property of a capacitor, like an inductor, is to store energy. It receives energy, stores it, and releases it back into the circuit at a later point in time. So if we connect a capacitor at the output of our rectifier circuit, capacitor will start charging. So it will charge. The first half cycle is going to charge. Let's say it charges from 0, right? Capacitor doesn't have any charge. You flip on the switch, capacitor starts charging. When the voltage starts going down, so this is when it's charging. And this is the portion when the capacitor is discharging because the voltage is now going down, meaning effectively the voltage is flipped opposite to what the capacitor voltage is. Okay, so capacitor starts discharging, and depending on the size of the capacitor, this is 0 volts, say 0 volts, and let's say this is some 5 volts, let's say randomly. So eventually the capacitor will reach 0 volts. It will discharge everything that it has. But if you use a large capacitor with a very long time constant or high time constant value, that discharge rate is going to be very slow. So what happens here is, if the discharge rate is slow, before it can discharge even, I want to say less than 10%, not even, in real life, it's like less than 1% of its value. The next charging cycle arrives and it begins charging again. And so you have a constant charge, discharge, charge, discharge, charge, discharge cycle. And then you have reduced, not reduced, but you have taken your AC voltage and you have converted into almost flat DC voltage. However, the surface of that waveform looks like the surface of the ocean waves rippling through. Hence, it is known as a ripple. Ripple voltage, VR. And typically, if your output's like 5 volts or 10 volts, your ripple voltage is in millivolts, far less than 1% of the overall. There's still a slight ripple, but far more than what we have with just pulsating DC. And that is the third step in a power supply. It's 3 o'clock. If you have to leave, you can leave. I'm just going to go on for a couple more minutes. So that's the ripple voltage, but that's still not quite the flat DC line, right? That's still not quite the flat DC line. So what we do is we attach the output of the capacitor to a voltage regulator. We need to regulate that voltage, meaning the output voltage should not change, not even the ripple. And so an actual DC supply, the simplest of DC supplies, have 4 parts. There's a step-down transformer. There's a rectifier circuit. There's a filter. And there's a regulator that provides the final flat DC line. The transformer, of course, will take it out. The components could be as simple as this. 1 diode rectifier, 1 capacitor filter, and 1 Zener diode regulator. This is the rectifier. This is the filter. And this is the regulator. And that's your V out. Okay, that's your V out. You had a question? Okay, question being asked is on the bridge rectifier circuit, do we need to account for both diode? Absolutely. Every single diode that's in the pathway needs to be accounted for. So it'll be 1.2 volts. It's in the center tap, it's only 1 diode every single time. It's only 1 diode. That's true. So the question being asked is, as a circuit designer, how do you account for that? Well, you work backwards. So if we want V out to be, let's say, 5 volts, then I need my Zener diode VZ input to be at least greater than, I would say, even at the lowest end, it should still be greater than like 7, 8, just to be safe, like 8 or 9 volts. So like 9 volts perhaps, maybe even 10, doesn't really matter. So 9 volts, that means your capacitor input, depending on the ripple that we obtain and the size of the capacitor input should be maybe a couple of volts higher than that, perhaps. So maybe 11, maybe 12 volts. And the capacitor input is 12 volts, and our bridge rectifier circuit has 2 diodes each. Then our diode input should be at least 15 volts coming from the transformer. So if you want to obtain 5 volts at the output, our input would be like 15 volts, which would be easy to do. It's just the number of turns in the secondary coil, so it doesn't really matter. Yes.
So like in the power supply in the lab, when I turned it out, the regulator.
So the question being asked is, in the lab power supplies, those are complicated designs. So without looking at the internals, I don't know what we are actually changing. There are solid state controls. There's a device called SCR, silicon control rectifiers. There's another device called a triac. A triac provides a solid state device to control the output voltage. So depending on the design, it could be anything in there. Yeah. All right, we'll end class here today, and we'll pick up here again on Friday.
Did you see what any class here today?
Wait,
Was there a question online?